Hello, my name is Paul Nussbaum. I'm a professor here at Ecpi University, and today I'd like to talk to you about engineering precision. So as you can see, we're in a electronics laboratory, and we do a lot of work with building and repairing electronic equipment, designing, and going ahead and troubleshooting things like that. We deal with engineering precision quite a bit, but no matter what field of engineering you decide to go into, mechanical, electronics, biomedical, even pharmaceutical, you're going to have some sort of engineering precision in dealing with numbers. Not a lot of mathematics per se, but just understanding, how we work with measurement instruments. So we're going to be talking about today engineering precision. You can see an old-timey voltmeter. Used a needle to go ahead and show what voltage, a bunch of little tick marks, lines on it that look kind of like a ruler. It even had this mirror behind the needle. So if you saw the needle and the reflection of the needle, it wasn't lined up correctly. You had to kind of turn it until you go ahead and see both the needle and the reflection lined up. Then you knew the precision of your number was a little more accurate. Obviously, modern on the road kind of auto ranging voltage and multimeters will take care of a lot greater precision electronically, but even there you have to know how to read the individual numbers and what it's telling you, and you have to understand from the manual what is the precision of that measurement instrument that you're using. So that's really the topic of what I'd like to talk to you about today. So let me go ahead and share my screen here. I just wanted to show you a couple of pictures of what I mean by engineering precision. We're going to be talking about rounding numbers, number of significant digits. We'll be talking about measurement and also calibration. So when you round numbers, I think you all pretty much know what rounding numbers means. Rounding numbers, if it's here taking a look at this measurement, if I measured anywhere between 17.0 to 17.4, that blue stripe here, then I would round down to the number 17 if I was rounding to whole numbers. If I measured anywhere from 17.5 all the way up to 17.9, I could round up to 18. So anything with 5 or above, I would round up. The decimal being below a 5, then I'd round down. So that's and the same thing, you're probably quite familiar with it. If I had, instead of 17, it was 1.7. I just kind of crudely added a decimal place here on the screen. But you understand, it's the same thing if I wanted to round to the nearest tenth. So if I would round down to 1.7, if it was anywhere between 1.70 to 1.74, and I would round up to 1.8 if it was anywhere from 1.75 to 1.79, this yellow. So I just added a decimal point, and now I'm rounding to the nearest tenth instead of rounding to the whole number there. So when you do the worksheet that you'll be receiving to go ahead and just practice some of this stuff, it's very simple. That's what it's asking you to do. Just round either to the whole number or to the nearest tenth. So really more importantly, I think, is the significant digits. In other words, what is the number of significant digits that I have to decide? Because as an engineer, I'm going to have to decide myself, where do I round off my number? How many digits do I put in my number? So the number of significant digits is shown in this example on this ruler. For example, I can see that the tip of the pencil falls somewhere between 18.7 inches and 18.8 inches. I can't really tell exactly where it is, but I'm kind of guessing it's a little closer to the 18.7. I'll guess 18.73. So you can see that the number 3 in red is definitely a best guess. So one of those numbers I had to put a best guess because there weren't any dash marks there. So engineers always include that guessed digit whenever they write a measurement. So what I mean by that is when I, as an engineer, write 18.73 and another engineer reads that number, they know not only the value is my best estimate, 18.73, but they also know that whatever device I used, it only had markings for 18.7 and 18.8. And the engineer who reading it knows that I had to guess at that last number was my best estimate. So that's why I always include that digit that has a guess. I don't put multiple digits. I don't put 18.735. It would be unreasonable for me to think that my eye had the accuracy to see anything more than a single digit of guessing. So by speaking in that way, engineer to engineer, we know not only the number I'm trying to tell you and convey to you, but also a little bit about the instrument I use to gather that information. So the precision of an instrument is basically that level of detail that I can go to. If the pencil length turned out to be exactly like this blue marking on the 17, right on the nose, I wouldn't just say 17. I would say 17.00 as an engineer, because I want to communicate to you that there are markings for the tenths on the instrument I use to measure it, and that my best guess was that it nailed 17 right on the nose. So that was that last zero, the hundredths, the 17.00. So that's what I mean by the precision of the measurement device. The engineer is telling the other engineer, it's not 17 inches, it's 17.00 inches. It is right on the money there. And the reading engineer knows that only the last digit was my best estimate. Now, that's not the case in everyday language. So in everyday language, we usually don't write things down like engineers do. Most people would just say, you know, it's 17 centimeters long or 17 inches long or whatever the ruler is measuring. I wouldn't go ahead and say that it was 17.00 centimeters long. I might conclude that the pencil, if somebody just, you know, were telling me, oh, it's a 17 centimeter pencil, I might say, well, I don't really know what kind of device they use. They could be anywhere between 16.5 or 17.4. You know, it could have been anywhere in this range. Maybe these small markings weren't there. Maybe only these larger stripes were there, and the person had to guess. But actually, what if there was only a marking every 10 centimeters? What if it only had 1, 10, 20, 30, 40? And I had to guess the 17 of the 17. So if an engineer told me it was 17 centimeters, I would think that there were markings only every 10 centimeters. I hope I'm not confusing you, but the bottom line is that last digit is the last significant digit. It's the one that you had to guess because there weren't markings, and you really should include that last digit. The worksheet is going to ask you to look at a measure. It's going to have a photo of a measurement device, and you'll be answering a bunch of questions about that measurement device based on what I just told you. Now, everything I'm telling you is in the worksheet as well. It's all written out, so you don't have to memorize everything I'm saying. It's all spelled out for you. So yeah, just take your time, and the questions are fairly simple, but through filling out the worksheet, it'll kind of be cemented in your memory a little bit more than if you just listened to the video and that was the end of it. So I appreciate you filling out the worksheet. A lot of times you'll hear engineers and engineering technologists talk about calibration. So what is calibration? Calibration means that that instrument still has the precision that we think it does. So sometimes, usually not a ruler, but sometimes other instruments like that voltmeter or some other measurement instrument could get damaged. Maybe they fell on the ground, or maybe over time it lost its precision based on wear and tear. So the process of calibration takes some known measurement values, like I know this is 0 volts and I know that this is 10 volts. I'm using a calibration instrument, and I then go ahead and adjust my other instruments so that they are calibrated to that standard. That's pretty much what calibration means. And then usually after you're done doing the calibrating, there might be maybe a screw that you had to turn to go ahead and calibrate it on this old-fashioned voltmeter. Let me see if I can show you that big on the screen there. On this old-fashioned voltmeter, you could see that there was this calibration screw right here. You'd actually turn the screw to calibrate where the 0 volts was. So it didn't have a whole heck of a lot of calibration beyond simply where the 0 volts was. But there are other instruments that have different screws to calibrate and change markings. So we might put, let's say, a piece of paint on that screw after we're done calibrating it, so that if somebody were to later turn the screw and make it a different value, then you could see that the paint cracked. So if you ever see like a little dab of paint, sometimes it's red, might look like nail polish or something to that effect, and it purposely is made to look and show that it's been cracked if anybody ever turns the screw again. That's kind of a calibration seal, if you will. It's not made to prevent you from changing it. It's made to let somebody else see very clearly that something has been changed. Basically, the worksheet is asking you to talk to your friends and see where they may have seen that sort of a calibration seal. So that's kind of an exercise where I'd like you to actually talk to your family as well, even after the class is over, about a calibration seal, and bring that back with you next time I see you face to face. I'd like to hear what kinds of calibration seals they've seen over time. You'll find them on a number of things around, sometimes around your house and around everyday places, and you'd be surprised how many different kinds that people have seen. So I'm very curious. That's one of the worksheet questions. Where have you seen a calibration seal on something? So when we go ahead and manufacture something, let's say we've got these instruments, we've made these measurements, we are designing a new thing, a new toy, or a new electronic device, or a new cast for an injured person who's broken their arm, some kind of engineered thing where we design it according to some specifications. We don't often know for sure what the end result is going to be until we actually manufacture it. We can do all the math and do all the calculations, but sometimes when we go ahead and we make it in the real world, you know, the parts don't end up fitting together like we thought that they did. So we call this prototyping, and it usually is an engineering technologist that works with an engineer. So the engineer would do much more of the mathematics, and then the engineering technologist would know much more of what kinds of products there are in the world to make what the engineer has designed into reality. So the engineer might use certain numbers in designing something, and then the engineering technologist or the technician might try and actually build it and have to tweak some of the numbers. Just like an architect might design a house, but then the builder might realize, I have to build that house kind of on a slope, so I'm going to have to make one of the walls a little longer to reach the foundation, something to that effect. So we're going to use a calibration jig, and what that means is it's basically a trial run of a manufacturer. We're going to test build some things, and we're going to use 3D printing because it's fun and it's in the news a lot. It's a kind of manufacturing process I think we're going to see much more of as engineers, and I think as you move into your engineering field, both at the university and then beyond that into your careers, I think 3D printing is going to be a mainstay of not just plastics, but also biological materials, food processing may use 3D printing. So you'll see a lot more 3D printing. So we're going to do a calibration jig for 3D printing. And I'll give you this example here. A calibration jig is especially useful when something has moving parts. So it's one thing to build a model or a statue or something that's just nice and solid. If it's a little bit small in one direction or another, it's not a big deal. But if I have several parts that all have to fit together, or if I have several parts that need to either turn or they need to move together in a straight line, you know, they really have to fit together properly to make it function the way I want. So here, this picture is kind of an example of a child's toy, and it has this little thing on wheels that rolls to the left and right, and the wheels have these axles, and they have a certain diameter, and then this thing that rolls left and right has to fit into this kind of a slot, and that has this height h here. So we might, we might have to go ahead and understand a little bit about manufacturing, because I'll take the example of the wheel. The diameter of the hole of the wheel can't be exactly the same as the diameter of the axle, because if I make them exactly the same, then, well, they're not going to fit, are they? And then if I make them one of the axle much too small, then it's not really going to always stay in the center of the wheel. The wheel might be lopsided to one side or the other. So we really have to decide what difference should the diameter of the hole in the wheel versus the diameter of the axle, what should that be? And that decision might be based on our manufacturing process. So if I'm going to make it out of metal, am I going to go ahead and pour molten plastic into a mold? Or in this case, am I going to use 3D printing to 3D print the wheel and 3D print the axle on which the wheel will turn? So calibration jig that you're going to be working with really looks like the picture shown here. I go ahead and I create this special thing that I'm only going to use to test how things might rotate or turn. And so I'll make some sort of a device that has a hole in it. In this case, it has precisely a 4mm hole. And then I design a series of pegs, each one smaller than the other by a tiny bit. And when I want to design something and the engineer tells me I need it to be very hard to turn, open and close these scissors. I kind of want it to be tough to open and close the scissors. Or I want a pinwheel and I need it to spin really loosely, really easy to turn. I might have two different kinds of situations. One where I want it to spin very loosely, and another situation where I want the scissors to be kind of hard to open and close. I can go ahead and take that peg and try different size pegs and say, all right, well, that's the feel that I want for this particular device. That's how I'll manufacture it. I'll manufacture it a 3.8mm small, basically 0.1 or 0.2mm smaller than the hole, or whatever the difference is. That's kind of what we're going to use with the calibration jig. So the worksheet will have you doing a problem using this photo here and understanding which calibration jig, which peg size and how much bigger or smaller the diameter needs to be. So that's really the worksheet that I'd like you to try. It's all about engineering precision. It has a couple of exercises. I don't think they'll take you very long, but your teacher will have some things to talk to you about with them. That is pretty much what I wanted to cover with you today. I appreciate you watching this video. I'll be with you on alternating days, even and odd. So I'll be with you on Fridays for this portion. And I'm glad that you're able to watch this video and go ahead and do that worksheet. And I appreciate it. Once again, Paul Nussbaum over at ECPI University. It's nice seeing you virtually on the camera, and looking forward to seeing you face to face. All right, thank you very much.